This is the second video in our 3-video series about periodic trends. Today, we're going to talk about ionization energy. Ionization energy is the amount of energy required to remove the most loosely bound electron, or valence electron, from a gaseous atom in its ground state, which basically means the atom has to be a gas, and ground state means that the electrons haven't been bumped up to higher energy levels. We'll talk about electrons that aren't in the ground state later in this course. The higher the ionization energy is, the harder it is to remove an electron. How easy or hard it is to remove an electron depends on the effective nuclear charge, which is related to the number of protons in the nucleus, as well as electron shielding. The second thing is the Coulombic force, governed by Coulomb's law, which increases as charges get closer, decreases as charges get farther away, and increases as the charges get larger. Different amounts of energy are required to remove subsequent electrons. We define the first ionization energy as the energy required to remove the most loosely bound electron. The second ionization energy is the energy required to remove the second most loosely bound electron, and the third ionization energy is the energy required to remove the third most loosely bound electron. And we can actually go on and on and on till we've ripped off all the electrons. Let's talk about some general trends. It's easier to remove a valence electron than a core electron, and this is because valence electrons are farther from the nucleus. And because of the increased distance, the Coulombic force is lower than it is for a core electron. Core electrons also tend to be in full shells, and full shells are very, very stable. It's easier to remove an electron from a large atom than it is from a small one. And that's because the farther an electron gets from the nucleus, the more loosely bound it is, the lower that Coulombic force. Now, the more electrons you try to remove, the harder it is to remove another electron. As you remove electrons, the effective nuclear charge gets larger. The positive charge of the nucleus stays the same as it was before you started taking off the electrons. But every time you take an electron off, you're also decreasing the amount of electron repulsion, thus decreasing some of the shielding. The remaining electrons feel more pull from the nucleus. They're held in tighter. And this means subsequent electrons are going to be harder to ionize. Ionization energy decreases as you go down a column because you're adding energy levels. Every time you add a new energy level, the electrons get farther from the nucleus. The farther from the nucleus an electron is, the weaker the Coulombic attraction, because the Coulombic force is inversely proportional to the square of the distance between the two charges. As you go down a column, there is also more shielding from the core electrons, but distance from the nucleus is the most important factor responsible for these trends you see in the columns. Ionization energy increases as you move across the row of a periodic table. As you're moving to the right, you're adding more protons and more positive charge, but the shielding stays about the same because all of the valence electrons have the same core electrons. With the charge going up and the shielding being about the same, this means effective nuclear charge is getting larger as you move from left to right. As you may remember from our radius trends, as you go to the right, the electrons are pulled in closer to the atom, so you get a smaller atomic radius. It also takes more energy to ionize and remove electrons. You can see some of these trends in this graph right here. Look at the graph. What can we say about the elements that have the highest ionization energies? Pause and think a moment about this. You should notice that the elements with the highest ionization energies are the noble gases. They have full valence shells, and this is a very stable configuration. It's one of the reasons that noble gases are not reactive. They don't like to give up electrons. They don't like to take electrons. They are happy to be who they are. Now, the easiest elements to ionize are the group 1, the alkali metals. They're very happy to give up an electron. And when they do, they end up with a very stable electron configuration, just like a noble gas has, with a full shell of valence electrons. So if you look closely, you'll see these general trends of the ionization energy increasing as we move across a row from lithium to neon, and then from sodium to argon, and from potassium to krypton, and so forth. However, you may also notice that there are some strange little blips where the pattern seems to break. And these variations have to do with the subshell structure. Let's take a look at boron, aluminum, and gallium, which have ionization energies that are a little bit lower than the atoms preceding them. Well, it turns out that atoms that have partially filled shells give up electrons more easily than atoms with filled shells or filled subshells. As we take a look at these, we see that boron, aluminum, and gallium have partially filled p orbitals. The elements to their left, beryllium, magnesium, and calcium, all have filled s orbitals, and this makes them a little bit more stable than their next-door neighbors, and a little less willing to give up an electron. Now, there's also some variation with oxygen and sulfur, and this has to do with subshell structure as well. Now, if we take a look at the electron configuration and orbital notation for nitrogen, we see that we have a half-filled 2p subshell. But when we get to oxygen, we have to add another electron, and that has to go into a 2p, and we have to have 2 electrons that are doubled up. This is a little bit less stable than the configuration for nitrogen, where we had 1 electron in each of the p orbitals. This is why that electron is easier to ionize or remove from oxygen, and we see this trend in the graph. The ionization energy is a little bit lower. Another thing you need to know is that there is a higher ionization energy for each successive ionization. And this means that every time you pull off an electron, there are fewer electrons left to repel each other, and yet the number of protons attracting the electron stays the same. So the effective nuclear charge is increasing, and electrons are pulled more tightly to the nucleus. You can see it in this chart where IE1 is the first ionization energy, IE2 is the second, and so on and so forth. As we take away more electrons, those ionization energies go up. Now, if you look at this table closely, you will see some places where the ionization energy really jumps up compared to the energy before. So let's look at potassium as an example. The electron configuration for potassium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Now, according to our table, the first ionization energy is 418.8 kilojoules per mole. And once we remove that electron, our electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6. So now we have the same electron configuration that the noble gas that immediately precedes it, that would be argon, has. And noble gas configuration is pretty stable. So we can see that our second ionization energy is much, much higher than the first one. We go from 418.8 to 3051. And that's because if we want to ionize this, we have to pull an electron out of a full shell. And that is not an energetically favorable or easy thing to do. Now, let's look at calcium. We'll write out the electron configuration: 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. Now, the first ionization energy is 589.8 kilojoules per mole. And if we pull off an electron, we have a 4s1 in our valence shell. Now, the second ionization energy, 1145, it's bigger. It's about twice as big as the first one, but it's not a huge jump because it's not terribly difficult to pull off that other 4s electron. Now notice, after we've done our second ionization, we have pulled off the fourth principal energy level, and we are now dealing with a completely filled third energy level. This calcium ion now has the same electron configuration as argon does. And this configuration is very, very stable. If we want to pull off another electron, we have to put in about 4 times the energy that it took to pull off the last electron, because we're having to remove core electrons. That is not energetically favorable. It is difficult to do. And if we look at the other places in this table, we see several other very big jumps. And you can bet a lot of these big jumps are happening because at that ionization level, you have to pull off a core electron, and that's not favorable. Why do we care about ionization energy? Well, understanding ionization energy is important when we want to predict what kinds of bonds an atom will form. For example, ionic versus covalent. So let's summarize. Ionization energy is the amount of energy required to remove the most loosely bound electron from an atom in its gaseous state. How easy or how hard it is to remove an electron is going to depend on the effective nuclear charge, as well as the distance the electron is from the nucleus. Energy is always required to remove an electron. Valence electrons are easier to remove than core electrons. Ionization energy decreases. It's easier to move electrons as you are going down a column towards larger atoms, which have valence electrons farther from the nucleus. Ionization energy increases as you move left to right across a row. Because you are adding more protons and the effective nuclear charge is larger and holds on to the electrons more tightly, we can see some ionization energy trends in graphs. And from ionization energy tables like this one, you can see that with successive ionizations, you have to put in more energy. And there are large jumps in energy when the next electron you need to ionize is a core electron.